go ahead with our next session. The topic, hydrogen. I'd like to call upon our session chair, Dr. B. Ravi Kumar, CJM, CREC, DPCL. Request Dr. Ravi Kumar to please join us. Our speakers, Ms. Ritika Gaur, Project Head, Marketing CEO, Sohat. All right, ma'am. She's the Project Head, the Soitec. Green hydrogen using photoelectrochemical technology is the topic she's going to be taking. I also request Mr. David Chastain to kindly join us. He's the professor at UCLA. The topic that we will be speaking on is producing hydrogen while capturing CO2. Clean hydrogen production with integrated CO2 capture is the topic that will be covered by Mr. Marcus Letzman, Director of Business Development, GTI Energy. Low-cost alkaline exchange materials process would be covered by Mr. Nicholas Scott, an investor for Ecolectro. And finally, electroactive microbial biohydrogen by Mr. Kamar Suhail Bharta, the CTO and co-founder, Oxys Biorenewables. We regret to announce that we would not have Mr. Roshan Sinhan join us today from Nucleus. He would have been speaking on the topic membrane-less hydrogen electrolyzers. Well, we will now hand over to our session chair to take it from here.
Welcome to hydrogen session. Happy to be part of this scale conference. Solving for climate action by leveraging ecosystem. I understand different startups are going to discuss two novel approaches how to solve the climate issues. We have been dependent on hydrocarbons in one form or the other, mainly for fuel and energy purpose, and subsequently for solvents, plastics, fibers, and there are lots more applications. We cannot live without hydrocarbons. But we have to minimize the environmental impact. We all know the CO2 emissions are going to go up. We continue to use fossil fuels, and we have to look for renewable options. And today we have got 6 startups who are going to discuss implement innovative approaches, how we can overcome this particular problem through green hydrogen production and cost-effective solar fuel and power production using photo-electrochemical pathways, energy transition solutions for improving lives and environment, membrane technology for green hydrogen production, biohydrogen production technologies. And let us hear from how they are going to bring down the cost. One of the main reasons why these technologies have not taken up so far is in a big way. The cost is a key concern. Last session I attended this solar-based electricity production. It is very surprising to note that in the last 10 years, India has adopted more than 50% solar-based electricity, and in next 10 years it is going to touch 75% or something like that. And soon, even petrochemicals and hydrogen and energy use, we are going to see the same kind of scenario. And these startups are very, very vital. And let us hear what they are going to, how they are going to bring down the cost. Now I invite you are the boss.
Very good afternoon, everyone. My name is Ritika. I'm from the strategic marketing team of SoHitech. So today, unfortunately, our technical person is not available. If you have any questions and queries, we can take it at booth number S41. Moving further with the presentation, SoHitech holds the world record in terms of producing green hydrogen. After 10 years of research and development and 150 years of combined experience of the core workers of the team, we have come up in the market with a product known as R. As we all know that the world is on the transit mode from conventional fossil fuel to new renewable source of energy, that is hydrogen. Hydrogen, one of the cleanest fuel of the future, and is very high in terms of its demand. Earlier process, 96% of the hydrogen was produced by centralized method, and it was by the burning of conventional fossil fuels. So what SoHitech has exactly brought up in the market? SoHitech has come up in the market with a product known as R. R is an artificial tree which works similar to a living tree. R is named after, in Latin, it is known as a tree. So basically the technology is quite simple and advanced. The technology is, we concentrate the sunlight, we do have a reactor present in the top of the solar panel which converts the concentrated sunlight into electricity, and further we are splitting the water into two parts, that is hydrogen and oxygen. Moving further, this whole technology is known as photoelectrochemical process. It is one of the groundbreaking technologies so far, and of course 2 times more effective, twice times less in terms of space taking, and of course it's a plug and play technology which has entered in the market. Here I wanted a small glimpse of a CEO, Saurabh Tambune, who is an ex-IIT in Mumbai, right, who is the main mind setup besides this technology. So can you play the video, please? So going further with the presentation, as you know, one single hour saves up to 80 tons of carbon dioxide per year. When I say one single hour, that means the smallest hour, which is of 9 meters, saves up to 80 tons of carbon dioxide per year. So how are we scaling up in the market? We are scaling up in the market, we are coming up in the garden of arts and forest of art. 50 plus arts are known as garden of art, 100 plus arts are known as forest of art. Of course, talking about the durability of the product, it is of 25 years and as I said, 2 times more efficient, 2 times less space taking, and of course saves up to and cheaper in the market price 30 to 60%. Talking about the product readiness level, you can see the product R has already reached the green immersion zone and is mature and ready as photovoltaic humidity and electrolysis. We have come up in the market with 3 segregations, 9 meters of R, steel shirt. No shoes. We have come up with the market with 9 meters of arc, 13 meters of arc or 25 meters of arc. 9 meters produce up to 10 kg of hydrogen per day, 13 meters up to 20 kg of hydrogen per day, and of course 25 up to 80 kg of hydrogen per day. Going our offerings, we develop, build and operate. When we talk about the garden of our art, the customer invests, customer owns, forest of art, fuel and power and service to the customer. Moving further, talking about the product positioning, you can easily see that as per the sustainability, the product is very high. As per the pricing, the product is already at a very low. This is a small pilot project running in Europe itself or one of the industrial projects. You can have a glimpse of it. Moving further, initially in the starting of the conversation I said, we hold the world record. We have recently been awarded as the Best Technology Award in Morocco. Going back, it's a Swiss technology, Swiss innovation, everything takes place in Switzerland itself. These are the main mindsets besides this technology who are present in Switzerland office. We do have an office in Delhi in itself. So in the end of my presentation, I would like to say our mission is to empower nature by making today's the solution of tomorrow. By mimicking the nature, our vision is to create technologies for solving current energy dependency. Thank you.
Hello, everybody. My third time up today. The slides are somewhat based on my previous presentation, so you'll hear some of it. I'm here representing Aquatic, which is a spin-out company from UCLA, Institute of Carbon Management. So Aquatic powers the green economy, and our technology is based off of seawire electrolysis that will couple carbon dioxide removal with the production of green hydrogen, so long as we are using green electrons, renewable electrons, to drive the process forward at the lowest cost. So, as I stated earlier, we are at the precipice of a very exciting time in these industries. The global carbon dioxide removal market is expected to grow to about $1 trillion by 2050. Green hydrogen, energy decarbonization industry is expected to grow to about 1.4 trillion by 2050. It represents a tremendous opportunity for businesses to expand and for new technologies to be developed and utilized across the world. And our entire business is based off of the premise that there's really two challenges that are happening at the same time. The first one is ending our reliance on fossil fuels, as our person who introduced us mentioned earlier. And the second one is removing legacy CO2 emissions. And we are interested in both of these challenges. And the product's goal is really to answer both of these challenges, specifically by producing green hydrogen through a seawater electrolysis process, which I will elaborate in a second. And of course, the second one is by actually removing atmospheric CO2 and sequestering it safely in a stable format. I guess I got it here. I do want to say something important. Every single IPCC scenario says that we have to actually remove CO2 from the atmosphere in order to minimize the impact of climate change. It's not enough to just stop emitting. Even if we stopped emitting today, if we had a magic wand and we could stop emitting CO2, we would still have decades of CO2 removal from the atmosphere ahead of us in order to reduce the impact of these legacy emissions. So regardless of how optimistic or pessimistic we are, when you're feeling about CO2 or CDR, we have to still draw down atmospheric concentrations of CO2. So our green hydrogen that we produce from our electrochemical reaction through Aquatic has two things that we do. So this first generates green hydrogen, and the second it actually captures and sequesters CO2, as I mentioned earlier. This is quite distinct from conventional or emerging hydrogen production. For example, if we're using PEM or alkaline electrolyzers, conventional electrolyzers, you will generate green hydrogen, that is true, but you will potentially be emitting CO2 if your energy source is not completely renewable. And of course, if blue or brown hydrogen, you will be emitting quite a bit of CO2. So the Aquatic process achieves both of these things. It generates green hydrogen and captures and sequesters CO2. That's an important distinction. If we look at our projected cost curve, it's bending nicely. We predict that by 2050, we will bring down our average cost to about $1 a kilogram. This is approaching the projections for blue hydrogen and cheaper than gray hydrogen, moving into the future. And if we, very importantly, for every ton of CO2 that we capture and sequester in the form of a mineral, stable mineral carbonate or bicarbonate ion, we will generate about 30 kilograms of green hydrogen. So again, this is a significant amount of hydrogen that is generated for every ton of CO2 that we capture. We have a commercial agreement with Boeing to provide them with 2.1 tons, 2,100 tons of hydrogen from our CDR process. And the pricing of the contract terms are in line with current market conditions. The potential co-location of 100 kilotons per year plant with an SAF refinery and hydrogen pipeline is also in the works. We are having ongoing negotiations with various industrial buyers for hydrogen. Hydrogen is very important for Aquatic's future economic prosperity. Hydrogen is a large established market. It's currently at about $250 billion per year. It's highly liquid and it's expected to grow rapidly in the next couple of decades. In terms of the demand is somewhat inelastic. There are industries that actually absolutely have to have hydrogen so we can meet that demand. The pricing is rather predictable. We can bank some of our, if we do have access, which we typically do, to very cheap renewable energy. For example, when there's excess capacity, we can bank that energy in the form of hydrogen and store it, and release it, either sell it or use it to generate energy for our CO2 capture process. Obviously, in terms of financing our future projects, having a predictable and reliable additional stream of income makes it easier for us to raise future funds. And these additional revenue streams, it just makes it easier for us to sell technology. If we actually look at our technology, as I mentioned earlier, our technology is quite simple. We take 4 inputs: seawater, electricity, rocks, and air. We combine them in an electrochemical process, basically a seawater electrolyzer that we develop. We generate an alkaline stream where we do our CO2 capture and sequestration, and a carbon negative hydrogen stream, which we can then either sell or utilize in order to reduce our overall energy consumption. In terms of offtake agreements, like I mentioned, we have commercial agreements with Boeing, and we've already sold them 62,000 tons of CO2 carbon credits. We are in the middle of a significant expansion. We have an agreement signed with the Public Utility Boards of Singapore, where we are building a 10 ton per day CO2 capture and sequestration plant that will generate a significant amount of hydrogen as well. And we are raising funds for building our production capacity for anode manufacturing facilities and electrolyzer construction as well. We have 2 pilot plants that have been operating for more than a year now, one in Los Angeles and one in Singapore. Image on the left is the plant in Los Angeles, image on the right is Singapore. And Singapore is tied to a seawater desalination plant. One on the left is in the port of Los Angeles, just drawing seawater. So we draw seawater, we don't really pre-treat it, and then we convert it to, like I said, an alkaline and an acidic stream, the alkaline stream. That's where the CO2 capture and sequestration takes place, and the hydrogen is generated. Our next step is to, like I said, build a 10 ton per day plant in Singapore. Here are the mock-ups of the plant. You can see the electrolyzers in the center that will generate the hydrogen, and off to the right you can see our hopeful hydrogen storage facility. In the interest of time, I'm going to skip this. Our ask from you is similar to my ask from the previous talk that I gave about an hour ago. We want to find partners in India that have access to renewable electricity with firm low prices. We want partners who have access to seawater, who have access to rocks, and potentially have access to hard to abate CO2 streams like the ammonia manufacturing or steel industry. Why you should partner with us? We are a very promising technology for scalable decarbonization of hydrogen production. We do it together, which is important. We have competitive advantage by building scale as a first mover. We have demonstrated our pilots for over a year now. These pilots are doing 100 kilos of of CO2 per day. We've demonstrated both the engineering and the chemistry. We are now moving forward for a 10 ton per day plant. That's a semi-commercial plant, and we have plans already by 2026 to build a full commercial plant, which is several thousand tons per day. We have fast value creation. We have first revenues by pre-purchases of both carbon dioxide and CO2 credits and hydrogen from large industrial entities. We have an excellent team that is driven by translating science into societal progress. We have a very strong IP position that is protected through the University of California with licensing agreements towards the product. And we're riding this mega trend of minimizing climate change, which we predict will drive growth for at least the next few decades. Thank you very much.
Now I invite Mr. Desai. So, Mr. Mark Desai, CDAS. So,
good afternoon, everybody. Thanks again for having me here, giving us the opportunity to present some technologies here for the energy transition. I showed this slide before, so I keep it short this time. GKI Energy is a leading research and technology development and training organization, really dedicated now to the energy transition. We take that very seriously. We have about 500 people based in the Chicago area, in the US, and really want to innovate and commercialize and implement technologies. So we take that very seriously. We do that a lot in partnership with other organizations, sometimes with individual partners, sometimes in larger collaborative arrangements. So the technology that I want to talk about here is, of course, in the hydrogen session. Hydrogen in a sustainable energy system, hydrogen will probably play a major role. A lot of investment goes into electrolysis. There's a big rollout that's being expected. But we also believe that natural gas-based hydrogen with CO2 capture will play a major role. So the data that we see here is from the IEA Global Hydrogen Review a couple of years back, so things might have changed a little bit, but not fundamentally. On the top right, you see in blue, light blue, the expected hydrogen production by electrolysis over the next few decades. And what we can also see is in yellow, the portion of hydrogen production, conventional hydrogen production, but with carbon capture. So currently, almost all hydrogen is really being produced from natural gas. That, of course, has a big CO2 footprint. So but it's really the lowest cost option, right? So really addressing that CO2 footprint, that is what's really necessary. So why is it that natural gas-based hydrogen will play such a big role? The reason is simply cost, right? So when you see here the expected cost of the next few decades for renewable hydrogen is still very high. Currently, renewable hydrogen is 3 to 10 times as expensive as natural gas-based hydrogen. Over the years, with an increased penalty on CO2 emissions, with parts of the world, the cost of hydrogen production from fossil resources with unabated CO2 capture, emissions is going to go up. So CO2 capture solves that problem. So we believe that natural gas-based hydrogen, you see here in yellow in the middle, natural gas-based hydrogen with CCUS will be the lowest cost option, really for the foreseeable future. So this is where our hydrogen technology comes in, which is a natural gas-based hydrogen production with integrated CO2 capture. I know this graph looks a little bit complicated. It's a little bit hard to talk through it without a pointer. But what I do want to point out is that on the top you see actually the reactions that take place. So absorbent enhanced reforming. What happens is that you have a catalytic process, you reform the natural gas, and you produce hydrogen. In the same reaction, you produce CO2. The difference that we have here is that we have a sorbent in the catalyst, and that sorbent absorbs the CO2 while it's being generated. Okay, so you're doing the CO2 capture inherently in the process. It is not an after solution after the process. It happens inherently in the process. And what happens then is that the sorbent gets carried out with the catalyst product. You separate it, and you can regenerate the sorbent, release the CO2, and put the sorbent back into the process. So essentially what you've done is in a very efficient way, a very compact reactor system. You've taken natural gas and you create a hydrogen product stream and a clean CO2 stream, all in one process. The process is also very close to being heat balanced. That's also an advantage. The technology development has been supported by the US Department of Energy over the last several years. We've developed a pilot plan, and you see here some schematic and then also some pictures. The operations of that started last year. We have some successes really in there, so we've done all the solids circulation in that pilot. We achieved the design rate for the solid circulation and also achieved the expected hydrogen production. So overall, pretty tall facility. It's a vertical reactor system. You see that here. It's about 4 stories tall. So that pilot is operating. We're still expecting to do much more long-term operations. So it's catalytic absorbent process technology. One of the fundamentals is always long-term operation of that, which we're currently doing. What we're also doing is there is a larger pilot project, about 20 times larger than the one that we have in the US. And this one here is actually hosted at Cranfield University in the UK. It's funded by the UK government. And has capacity of about 1 megawatt thermal hydrogen production. So that translates to just under a ton of hydrogen a day. So this is a very substantial facility that has been in construction there. The idea is, the objectives are really to demonstrate the first scale-up step from the previous pilot to make sure that all the components, valves, and whatnot, catalysts and all that is really ready for scale-up, and then also achieve with this pilot sufficient operating conditions, operating hours, and experience, so that we actually can go to a much larger pilot in the future. So the unit has been commissioned. They're really in the final stages. I wish I had some operating data to share. It's not quite ready yet. So our team of engineers will actually go to the UK next month and start up that system. So we'll be operating this in Q2 of this year. Here you see some other pictures of that. Very substantial investment going into that technology. There's a picture on the left again. So it's a pretty tall system, vertical system, but that's how the riser reactor is being configured. In the middle picture, you actually see the reactor itself. little bit about the economics of this. So here you see the levelized cost of hydrogen. So those are the blue bars to the left scale for conventional steam methane reforming with CO2 capture, and then autothermal reforming with CO2 capture. So those are the conventional technologies. And the three cases on the right are actually cases for the GTI technology, but at different CO2 capture rates. And we can go all the way up to 98 plus CO2 capture. And what you see is that compared to the conventional technologies, our technology, because it's so compact, has a much lower levelized cost of hydrogen. And the difference is really mainly due to the CapEx, because our process doesn't do the CO2 capture as an afterthought process. It's really CO2 capture that's inherent in the process. So that leads to that very compact system and to the low capital cost and consequently to a low levelized cost of hydrogen. And in the green bars, you also see the carbon intensity of that hydrogen that's being produced. So as you go to higher CO2 capture rates, of course, you can achieve much lower carbon intensity. That's what you want. But it also comes at a cost. So the levelized cost of hydrogen then also goes up. So that really is an economic question. It's not a technical question, it's really an economic trade-off that one has to make when you operate such a system. So in summary, the GTI hydrogen generator with integrated CO2 capture has been developed with proof of concept to the current pilots that I showed you. 20 to 30% lower hydrogen production cost versus conventional SMR with CO2 capture. 40 to 50% lower CapEx current technology. So this is not a small change. This is not a 10% improvement. It's really fundamentally different, much lower capture, much lower cost. More than 80-90% of CO2 capture is possible, and significantly lower carbon intensity. So we believe this is an enabling technology for multiple low carbon markets. For power and hydrogen infrastructure, when we're feeding hydrogen to pipelines, but also industrial heat. And then hydrogen, of course, also for existing applications. Hydrogen is used, as you know, in refining energy. With that, my time is up. Thank you very much for your attention. Some acknowledgements. There you go. Thank you.
Mr. Nick will present his membrane technology for reducing green hydrogen production costs.
Hi there. My name is Nick Gould, and I'm here representing Starshot Capital, a climate-focused venture capital fund based in California. And I'm also representing one of our portfolio companies today, Ecoelectro. That's a green hydrogen company we're really proud of. We have a stand in the second aisle from the left, just outside the hall. If you'd like to talk about Ecoelectro later, or any of our other portfolio companies. So with that, Ecoelectro enables cost-effective green hydrogen production at scale. That's their purpose and goal. Just a brief overview, their technology was spun out of Cornell's chemistry department by 2 PhD students who subsequently, after gaining their PhDs, ran off with this as a startup company. They have 7 patent families under this portfolio that covers their novel membrane architecture inside the anion exchange membrane electrolyzer, as well as the encapsulated entire stack device. The team has expertise in organic and polymer chemistry. It's one of the co-founders' PhD theses, where she found this and really developed this novel polymer material that came up with this durable membrane. And the other co-founder was a PhD student in electrolysis. So they teamed up and made this novel AEM device that has really similar performance to the more commercialized and traditional proton exchange membrane systems, but at much lower cost. And the key drivers of these lower costs for their AEM electrolyzers are are three things here. One, removing the noble metals that typically PEM electrolyzers use, notably iridium, as well as moving from titanium, which is generally needed in PEM electrolyzers to avoid serious corrosion in acidic conditions, and using stainless steel instead. And also, what's really unique here is getting rid of fluorinated chemistry from the membrane. Most membranes within electrolyzers today, such as Nafion, are perfluorinated. It's a class of chemicals that's coming under increasing legislation to kind of phase out because of its health and environmental effects. So their technology avoids that complication. The hydrogen market, as we all know here, is growing really exponentially. Electrolysis is one of the key ways to scale it up. But a lot of these more commercialized technologies like PEM and the old alkaline units really have some notable challenges, technical and cost-wise. So here I'm outlining some of those. This is kind of a dense table, so I highlighted the most important parts in red to focus on. The two, these are really the competing technologies that Ecolectro's trying to reduce the costs of. And the two on the left are the most commercialized, an old alkaline electrolyzer and a PEM electrolyzer. These, the furthest along, the alkaline's often preferred or sometimes preferred for its low cost, but has low current densities. So that's kind of a stand-in for the hydrogen production rate per unit area. So they tend to be kind of large because they have low current densities. If you want a certain hydrogen production rate, you need to scale it up larger. They also have pretty low response times for startup and shutdown, so they're a little tough to integrate with renewables, which tend to be intermittent. PEM was largely, just a little bit more expensive than alkaline on average, but has this advantage of higher production rates. It also has an advantage of being, easier to start up and shut down without renewable electricity, but it's expensive because of the noble metals, the fluorinated membrane, and so we're looking to find a new solution. And another technology that's maybe a little further behind in development that has active research is solid oxides. Today they're still pretty expensive, but they're interesting because they have a high theoretical electrical efficiency. But they operate at very high temperatures. This comes with some technical challenges of keeping it hot. When you cycle it, it tends to lose some durability if you have to turn it off and on again. But we can talk about that after the session if you'd like to know more. Ecolectro's technology is in a new class that's also area of research. It's a little less commercialized, and that's in the alkaline exchange membrane category. They're targeting a stack cost of less than $200 per kilowatt. Their efficiencies are similar to PEM. Really, the performance is similar to PEM in terms of current densities, startup shutdown flexibility, but the big challenge with AEM that has limited it thus far is its durability. And that's a lot of what attracted us to Ecolectro, is that they came up with a novel solution to that durability problem. Right, so here I'm showing you a graph of their durability in essence. So the y-axis you can take as a stand-in for the catalytic activity over time, where their membrane in green at the top, and this is over a day on the x-axis of active operation. You'll see after about a month of active operation, and their membrane is still holding strong, compared to a lot of their competing membrane technologies that are falling down off the graph and deteriorating. So to get more into the unit economics here, here in green I'm comparing Ecolectro to the PEM. There's some aspects of the eventual hydrogen production costs that are constant across electrolyzers. Balance of plant is like the compressors and pumps and chillers and power supplies, not actually where the chemistry is happening. Right? And OpEx is an efficiency and electrical and electricity price stand-in. But they can really reduce that stack cost, which is really where the chemistry is occurring, by, like I said before, removing titanium, going to stainless steel, getting rid of iridium, and their membrane itself is already cost competitive at the lab scale with Nafion. So once it scales up, we're optimistic that it'll also be much cheaper. Just a bit of a sensitivity analysis on those costs I want to mention, because this is a key assumption. We assume here, compared to the PEM cost, you see Electra, I have about $1.33 per kilogram at 1 cent. So that's the cheap part of renewable during the day as it fluctuates intermittently. Up at about 4 cents, that price goes up to about $2.50. Right, and just one more time, similar compared to PEM, similar efficiencies, similar current densities and production rates. This 4.5 is actually really high, if you're familiar with this field. That one, that value does have a small loading of platinum in with the nickel. With just a pure nickel catalyst, it's about half that, which is on the upper end of PEM hydrogen production rates. They're considering and thinking about offering both the all nickel and nickel with some platinum, just to offer both products. Just to reiterate one more time, their real novelty here that came about because of this novel membrane is moving away from titanium to stainless steel, getting rid of noble metals, and moving away from PFAS and those legislative problems that are potentially coming down the line in the near future. So today, this last year, 2023, they successfully developed their 10 kilowatt scale electrolyzer that's roughly 5 kilograms per day. This current year, they're working on a single stack going up to about 100 kilowatts. It's more like 50 kilograms per day. And next year, they hope to get up to the megawatt scale. That one probably will be a few stacks in parallel. So to summarize, I just want to give some logistics details about their operations. Their organic chemistry synthesis processes are pretty common, so there's nothing really outside the ordinary there in terms of how they make the membrane. But of course, today they're a Series A company that's still lab scale on kilograms scale. They're looking to partner with companies to scale up that manufacturing soon. And they're interested also in understanding what the supply chain essentially for the membrane, how they can potentially source different raw material chemicals that build out the membrane and improve their supply chain there. So a lot of what they're looking for here, and please talk to us later if you're interested. They're looking for expertise in scale up of their organic and polymer chemistry. So that's both building up the monomer and then polymerizing that monomer. Of course, they're looking for customers in the green hydrogen space. And they're looking for some knowledge and know-how in the raw materials and inputs to make the membrane material. They've successfully recently started their roll-to-roll processing and membrane manufacturing, so that's going pretty well, at least for an early stage company. So any expertise there would also be helpful. And they're also investigating increasing the strength and mechanical strength of that membrane by using some additives and supports. So that's also of interest to them if you have that know-how as well. So with that, thank you. I hope you liked our intro, and I'm happy to take some questions after the last talk.
Thank you. Now I invite
sitting on a vast resource in the form of wastewater rich in carbon content. At Oasis Biorenewables, we have developed bioreactors that use this carbon content in wastewater as feedstock to generate hydrogen. Native microbes sourced from wastewater are used as biocatalysts to break this carbon content down as a precursor to hydrogen generation. Currently, the reactors are deployed across the nation at different sites. These reactors have helped our customers reduce their costs by over 90% and also secure their supply chain. OSIS envisions every industrial site generating their own hydrogen on-site, on demand.
Yeah, thanks. Oh, okay, here on. Right, there was a short video, a small intro about OSIS. For India to meet its GHG targets by 2030, my slide is not moving. To meet its targets by 2030, hard to abate industries like oil and gas, steel, manufacturing are the most obvious first choices to decarbonize. However, as of today, they are hardly attractive alternate sources of energy like green hydrogen simply because the economics don't make sense. Incidentally, these are also the industries that guzzle a lot of water. Last year alone, we produced 44 billion cubic meters of wastewater in form of industrial effluents. At OSIS, we have turned the narrative around. We have made green hydrogen available today and affordable today using wastewater as feedstock that is available on site. Let me introduce to you OB Hydrocell, an intelligent bioreactor that uses the organic content present within the wastewater to generate green hydrogen instead of splitting pure water. The OB Hydrocell can be installed on site at the vicinity of the application of hydrogen, therefore not having to compress and transport hydrogen. The required hydrogen is produced on site on demand, and the power that is required to generate this hydrogen is extremely low simply because majority of the work is done by the biocatalyst and not by splitting water. At the heart of the system are the biocatalysts and the electrodes. Exoelectrogenic microbial communities at the anode break down the organic content, and while doing so they release H+ ions from the organic content, and in their respiration they also emit CO2 and electrons. These H+ ions and the electrons that is emitted by the microbes combine at the cathode to give you hydrogen. Half of the process is biogenic and the other half is electrochemical. The biocatalysts are developed in-house. Every wastewater is unique, and our mission is to derive the highest possible yield for each and every one of our customers. This is why we build biocatalysts from the source of the wastewater itself. A sample of the wastewater is taken to the lab where useful communities of microbes are identified and marked, and then they are concentrated using the same wastewater as a medium. And then finally what you have is a really potent bioconsortia that thrives on breaking down the organic content. This bioconsortia is then immobilized on the anode of the electrode which goes into the reactor. As of today, OSIS has grown its technology across various sectors like oil and gas, steel, specialty chemicals, food and beverage. We have been deliberate in deploying our technology across a diverse set of customers. All these sectors have abundant wastewater and enormous energy needs. Next up, naturally, we have glass, refineries and textiles that's coming up in our pipeline. Our largest installation today is a 250 kg per day plant. We are also working with one of India's largest steel manufacturers in Jharkhand to go from a 30 kg per day pilot to a 1 ton per day plant. Adoption has been relatively very easy for us as a company, and our customers are happy to try our technology out simply because they do not have to pay for the reactors itself. They only have to pay for every kg of hydrogen that they use. Based on some on-site runs and also lab-scale studies, here are some projections of how much power we use to generate 1 kg of hydrogen, how much CO2 is generated for it, and also the price. So, as of today, the price is anywhere between 67 to 114 rupees per kg of hydrogen. Of course, the range depends on the complexity of the organic content that is there in the wastewater, the volume of wastewater that is available on site, and finally also the application of hydrogen. Before I conclude, I want to leave you with 3 questions. Why use pure water when you can use wastewater? Why not make it right next to where you use it? And the most important, why wait until tomorrow when you can get it today? My name is Suhail, and it has been a thrill talking to you about OSIS and our journey so far. Thank you for listening so patiently. If you want to get in touch, my QR is right there. I think it's half cut out by that, but my QR is right there, and please get in touch with me. Thank you.
open to questions. Do we have any? All right.
Hello. So I'm Subhash. I'm from TIS Mumbai, doing my master's in environment, climate change and sustainability. So I have a question for all of you. So everyone is now talking about white hydrogen, that is natural hydrogen. And in the case of Mali, we can see that the pressure of hydrogen is not going down even after 5 to 6 years of operation. So, can be the solution for all of our problems, like energy problems and climate problems? And what do you guys think about this white hydrogen hype?
I think that if they find enough of it, it would solve all our problems. The question is, will they find it? And so far, the case of Mali is pretty unique. There's a reasonable chance they'll find more deposits like that. It definitely looks like it's from superutilization of ferrous, the subsurface, high temperature, high pressure, actually carrying water. So it is renewable. And how do you get it out of the ground? I'm not sure. You know yet. I'm not sure if they're going to find meaningful amounts of compressed hydrogen in the tap. So I think we're in the early days of discovery. It's very exciting. I thought a lot of smart people have put pretty big bets on this. Good luck to them. Solve some of our problems.
Well, maybe just one other thing to add. When you think about hydrogen solving all our problems, I think that's very optimistic. And the reason is it's not only about the production of hydrogen. Handling the hydrogen, storing hydrogen, putting hydrogen into infrastructure and utilizing hydrogen, there's a lot of technical challenges that yet need to be solved with that. And so it's a pretty complex problem, really utilizing hydrogen in a very large scale and distributed fashion across the entire economy. It will take a lot of investment that goes beyond just the production of hydrogen. So it's not going to be easy.
Do we have any more questions?
This question is not specifically directed to an individual speaker, but taking leaf around how we could eventually make green hydrogen more cost effective so that you have better chances of universal adoption. Maybe your thoughts on how we can bring down the cost of hydrogen and what eventually would be a business model for the water that is specifically sourced for producing green hydrogen. Will it be seawater, municipal wastewater, or industrial wastewater? So what would be a sustainable source of the green hydrogen in future? So what are your thoughts on this? Thanks.
Very interesting questions. I'm going to request any of the speakers who are going to be taking it up, kindly hold the mic a little closer so that you're a little louder and audible. Thank you.
I can talk a little bit about the cost reduction, the wastewater or the water sourcing part. I might give away to someone else. Each of the hydrogen production technologies has their own challenges, right? So that bring down the costs. And there's so many solutions here, and each of them probably face their own novel challenges that are in their way. I tried to show one key example of why some of the leading or more established green hydrogen technologies are behind today, and that's steel chemistry dependent on noble metals and dependent on materials that are really corrosion resistant, and those are driving a lot of the costs for those kind of more established green technologies.
Thank you, Nick, for taking that one. We're just another one here.
Hi, Mr. Bashar. One question for you. So when you had observed the wastewater to hydrogen production, the higher bio content had helped you to produce more hydrogen. Just want to understand.
Yes, so as a thumb rule, dirtier the water, better the hydrogen, as long as there's no human waste in it.
Okay, so more oily waste and all those things
Yes.
helps you more in that.
Yes. More hydrocarbons, better yield of hydrogen from that volume of waste.
Thank you. Ms. Gaur, one question for you. What is the LCOH you had observed when you are having?
Sir, on a very honest ground, I'm from the management group.
Okay.
And we have a technical people available, but they could not make it for the presentation, so I'm the last one to
Okay.
get up from the company itself. So that's the reason I would really love to connect you with the technical person.
Sure. Thank you. Good day.
Thank you for that, ma'am. Please do help our participants connect.
My question is directed to Mr. Suhail. Question is, is there any limitation with respect to pH for water what you are taking, right? Because industrially either realistic or basic those contents. So is there any limitation if you can comment or appreciate your comment for that?
So we have worked with water that has a pH of 3 up to 10. So within that range, so far there is no constraints, but beyond that also I do not see anything being a problem. We are also working on spent caustic out of a refinery, so pH is not really a consideration. As long as the chemical oxygen demand of the water is above 500 ppm, it will be economically viable to use our technology.
Right, with that, I think we can hand over to our session chair to wind this session up for us. Please.
We had a lot of innovative solutions for hydrogen production and biofuels. So I'm really excited to learn some of the chemical engineering principles that have been applied for scaling it up, especially Mr. Nick's presentation and the presentation from Cornell University. So how these chemical engineering principles can be used innovatively and effectively for bringing down the cost by adapting to challenging problem of thermodynamic limitations. So using calcium carbonate for driving the reaction forward, and also fluid bed technologies, and also innovatively bring down the cost of catalysts. I'm really excited about these technologies. And also this aquatic products, they have talked about hydrogen production with reduced CO2 reduction. Now, simultaneously you reduce CO2 as well as produce hydrogen. This is this is innovative solution, and I feel it has a lot of future. This is this very interesting technology. So these are some of the learnings, and the session is very fast. I could capture only so little and so much to learn. Thanks, and I'm really honored to be part of this particular session. Thanks to the organizers for giving me the opportunity.
Thank you so much, sir. And over to you, Rohan, to please quickly hand over mementos to our speakers. We will immediately proceed with our next session, the topic being resource efficiency. I would like to just inform all our participants that we have bifurcating this session into two parts. So the main topic of the session was resource efficiency based water and energy. So the two parts, water and energy, we'll be breaking it. We'll take the first half with energy and then proceed to water. So we're just bifurcating it for better understanding. We'll have that going just in a very short moment. We're going to request you to please stay in your seats. And if you would like to help yourself with a cup of tea or coffee, then it's available just right behind our stage. You can pick a cup and get back to your seats quickly. So that would be done. Thank you.